Today we're going to continue talking about dynamic programming. Until this point, most of our dynamic programming lectures were focused on shortest path in graphs. Today we're not going to talk about shortest path at all, and we're going to see some completely different examples of dynamic programming. So the first example for today is what I call the longest common subsequence problem. It's a very classical problem. In the input, you are given two different strings, S and T. So my input is just two strings, S and T. And in the output, you should write the length of the longest common subsequence between these two strings. Or you can also write the longest common subsequence itself. Now, today we're going to distinguish between substrings and subsequences. So whenever I talk about a substring, it means it has to be contiguous. So for example, this thing, like hat is a substring of S, but a subsequence doesn't have to be contiguous. So for example, BEHATIS is a subsequence, but not a substring of S. Okay. So I'm talking about subsequences first, which means that I get to take letters that are not next to each other. So my input is going to be just two strings. And as the output, I want you to write the length of the longest common subsequence. So what is the longest string that is both a subsequence of S and a subsequence of T? You should write its length. Again, it can also be that I'm asking you for the string itself. So for example, if I want to find the common subsequence here, I can find this. I can say I take the O, then I take this E, then I take this N and this N, let's say, and I take this O and this O, right? So OENO is a common subsequence of both S and T. Is it the longest one? Probably not, right? So we want to find the longest common subsequence of S and T. Now, of course, we want to do dynamic programming, so I'm going to define some subproblems. And then the idea is that I'm going to put these subproblems in a topological order and solve them in that order. Generally speaking, in all of these lectures on dynamic programming, the hardest thing and the art is really how to define your subproblems. Usually after you define your subproblems, the rest of it is easy, okay? So here's the subproblem that I want to define. I'm going to call it, let's say LCS for longest common subsequence, but actually, let's say longest common subsequence. Let me write it like that. And I'm going to have two parameters, I and J. And basically, I'm going to say this is the longest common subsequence if I can only use the first I characters of my first string S and only the first J characters of the second string T. Okay, so this is going to be the longest common subsequence of my string S if I go from index 1 to I only, and my string T if I can only go from index 1 to J. Okay, so I'm taking a prefix of my first string, only the first I characters, and I'm taking a prefix of my second string, only the first J characters, and I'm saying what is the answer on these two smaller strings. That's the subproblem that I'm going to define here, and I'm going to show it with longest common subsequence of I and J. Okay. Now, of course, I need to have some sort of a recursive formula that somehow connects these things together. I want to somehow have a dependence between my subproblems. So let's try to see how I can get that. So I want to find the longest common subsequence for the first I characters of my first string and the first j characters of my second string. So just imagine that this is my first string and this is my second string. I'm saying I'm only looking at the first I characters here, and I'm looking only at the first j characters here. Okay. I want to find a string that is a subsequence of both of these. So I'm just going to look at the very last character here and the very last character here. Right? Now, my question is, does my answer, does my longest common subsequence contain these two last characters? It can contain them only if they're the same character. For example, if I have an A here and a B here, of course, I cannot take this A and this B, because A is going to be the last character of my solution, and B is also going to be the last character, and they don't match. So if these two last characters match, then I can say, well, let's put this at the end of my solution, and let's go and find a solution that uses only the first I minus 1 characters of the first string and the first j minus 1 characters of the second. Okay, so when I'm calculating this, I'm going to say, well, let's do this check. First of all, if the i's character is equal to the j's character, so if si is equal to tj, then this thing, my longest common subsequence, its length is just going to be 1 plus the answer that I had for I minus 1 and j minus 1. But what if they don't match? So basically, all I'm saying here is for the case that they do match. So let's say, for example, I have, this is my I, I'm looking at this part of this string, and let's say this is my j. So I'm looking at this part of the second string. And the last characters match. The last characters are A. So when the last characters match, I know that it's optimal to just match them, right? Because if I don't match any of these, let's say I don't use this A to match it with this one, then I have to say at least one of them is not in my solution. If none of them are in my solution, I can just add the A to the end and get a bigger solution. But maybe I had maybe another A that was matched to this one. But now again, just like the lectures on greedy algorithms, I can change. I can say match this one to this one. So in any case, if the last characters match, the ideal thing to do is to match them together and then just say find the answer for I minus 1, j minus 1, and add this one character to the end of it. But the nicer question is what happens when they don't match? So let's say this is my j, so the last character here is an h, and let's say this is my I, so the last character here is an s. Okay. My last characters don't match, so I can have at most one of them in my solution, right? Maybe I don't have any of them in my solution, but in any case, I cannot have both of them in the solution. And because I cannot have both of them in the solution, whatever my solution is, it's going to be either without the s or without the h. If it's without the s, it's a common subsequence for I minus 1 characters of s and j characters of t. If it does not contain this h here, it's going to be a common subsequence of the first I characters of s and the first j minus 1 characters of t. So it's one of these two cases, and I don't know which one is going to be better, but I can just take the maximum, right? So I say otherwise, the length of the longest common subsequence from the first I characters of s and the first j characters of t is just the maximum of the same thing, longest, why did I write it incorrectly? Longest common subsequence, right? LCSSEQ. So it's the maximum of the longest common subsequence of I minus 1j and the longest common subsequence of I j minus 1. Okay. So this is the recurrence relation that I have at this point. But, well, it gives me an obvious topological order, right? So here, the answer for I and j depends on the answer on I minus 1 and j minus 1. And here I have I minus 1j and ij minus 1. So the sum of I and j is always decreasing. So I can just sort them in any order, in any topological order that makes sure these instances are solved before this one. And I would have my answer. So I can just go for every I from 1 to n and then for every j from 1 to n, and it will work. Okay. But then what are my base cases? Well, the base cases would be when I have 0 characters, right? If I have 0 characters, either from the first string or the second string, then my answer is just 0 because I don't have anything to match, right? So I'm not going to write the base cases here, but just remember those. Now, what is my total runtime? Well, I can just have 2 nested for loops, and they just compute this, and they spend a constant time computing each of them. So it's O(n)². Okay. Let's code this. Longest common subsequence CPP. And let's say that I'm going to read 2 strings, S and T. I read them. And let's say my maximum length in this case is 10 to the power of 4 or something. And then I just need this array. So I have LCS_sec, which is an array of these proportions, max and min-max. Okay. Now, here's the thing. Here I was using indices from 1 to n, but in C++ it's 0 to n minus 1. Just to make them match, I'm going to add some dummy character at the beginning. You don't need to do this. It's just because I want to have the exact same formulas. Okay. Now I'm going to compute these things. So I'm going to say for every I from 0 to the length of S. Right. And for every j from 0 to the length of t. Now, I say if I is 0 or j is 0, then this value is 0. LCS_sec of ij is 0. I mean, you don't need to again write this part because it's automatically 0 at the beginning anyway. This is a global variable, but I'm doing it anyway. In the other case, I want to compare Si and Tj. So if Si is equal to Tj, then this LCS_sec of ij becomes 1 plus the answer on I minus 1, j minus 1. Okay. Otherwise, my answer on ij is just the maximum of my answer on I minus 1j and my answer on ij minus 1. Okay. And of course, at the end, I want to print my answer. So in the end, I would just say, write LCS_sec. So here's the thing. My original length was something, then I added 1 character, so it's now increased by 1. So it's like S.length minus 1, T.length minus 1. Let's see. Let me give it this 2. So okay, it says 10. Is this correct? I don't know. You can try and figure it out if it's correct or not. But the next question is, how do I actually find this longest common subsequence if I don't just want its length, but I want the subsequence itself? How do I actually find it? Well, I can go back here and I can track my steps, right? So what are the steps when I'm actually putting something into my answer? I'm putting something into my answer when I'm doing this one. When I see that SI matches TJ, and then I say that the length of the sequence for I to J is 1 plus the length of the sequence from I minus 1 to J minus 1. So I can just trace my steps back, and basically every time I look at this LCS sec of IJ and I ask, how did I compute this? So it was either 1 plus LCS sec of I minus 1, J minus 1, in which case I know that the character at index I of S and the character at index J of T are going to be in my solution. Or it's one of these two cases, in which case I know where to go to find my solution. Okay, so I'm just going to trace my steps back, and that's going to give me my solution. So if I want my solution, let me actually just write a function called trace. I say just trace it back. T that is -1. And this is what my trace function does. I have two numbers, n and m. Basically, I want to print the longest common subsequence of the first n characters of the first string and the first m characters of the second string. And all I do is that I check this again. So I say if Sn was equal to Tm. I have to put my S and T up here. If this was the case, I can just find the answer for I minus 1, J minus 1, and add this character to the end. Okay, so I would just say return trace of n minus 1, m minus 1, and then at the end of it, add this one character. Plus, I'm not sure if this would work. Let's see. I have to do a string. And here I just say int it. Okay. Actually, now that I think about it, I would prefer it if I, instead of returning a string, I just print it. Sorry. I always change my mind in the middle of the code. Okay. So I would just say if Sn is equal to Tm, first do trace n minus 1, m minus 1, and then write Sn. Okay. Otherwise, I'm in this case, the two characters did not match. Now that I think about it, it's better if I use I and J, so that's what matches that one. Sorry. So if Si is equal to Tj, trace I minus 1, J minus 1, and print Si. Otherwise, I know that when I was calculating this value at Ij, I took one of these two. But which one did I take? I have to figure that out. I have to see which one is the larger one. And I have to trace this larger one. Okay? So in this case, I know that Si is not equal to Tj. So I would say if this one was bigger, LCS sec of I minus 1j was bigger than LCS sec of ij minus 1, then trace this bigger one, trace I minus 1j. Otherwise, trace ij minus 1. Okay. Of course, this is now just going over my DP table and figuring out which was the optimal choice at any given point. But I have to also write the base case, and the base case is very simple. If I is 0 or j is 0, just return, don't do anything. Right? Now, if I don't have a bug, this should work. So I'm going to copy this, paste it. Okay, It says the length is 10, and this is apparently the answer. 4, 5, 6, 7, 8, 9, 10. Now, again, is this correct? Hopefully it is. I think the code is so simple, I hopefully don't have a bug. But let's see if we can find it in both of these strings. So it's O-E-N-E. So O-E-N-E T-H-U-T-O-N. T-H-U-T-O-N. Okay. And here I have O-E-N E-T-H-U-T-O-N. Okay. So the thing that it found is definitely a common subsequence of both of them. Hopefully, if we don't have a bug, it's also the longest common subsequence. So we can find the longest common subsequence in O(n) squared. During this course, I'm generally going to just focus on the lengths and so on, but you can always do the same technique. You can always go back and trace your steps and see how you got each of the maximum choices or minimum choices in your DP. And that actually tells you what the optimal solution was. This is a very common technique. Okay. Now, what happens if instead of the longest common subsequence, I asked you for the longest common substring? Okay. So this is my second problem. Or actually, let me first ask a very simple problem. So let's do longest common suffix. Okay. So my input is again the strings S and T. And as the output, you should tell me what is the longest string that is a suffix of both S and T. Okay. What is the longest common suffix? Now, in this case, the answer is the empty string, because even the last characters don't match, right? So there is no longest common suffix here. But if, let's say, I had this string only until this point and this one only until this point, I have this that as the longest suffix that is appearing in both of them. And honestly, finding the longest suffix is really easy. You start at the end of the string, you keep matching and going back until you find the first mismatch. Okay? So I don't know, it's not even 2 pointers, it's more like 1 pointer. But let's say it's a 2 pointers problem. So you can find the longest suffix in O(n), where n is the length of the string. And here when I said n squared, I'm just assuming that n is the maximum length among the two strings. It's actually O(n)m if I have strings of lengths n and m, right? Okay. So this is easy, but what if instead of doing this, you had to answer a bunch of queries? And so in the input, I'm first going to give you these strings, and you get to pre-process them, calculate some dynamic programming values, whatever. And then I'm going to give you a bunch of queries, and each query just gives you 2 indices, I and j. Okay, so given I and j, you have to say what is the longest common suffix if I only look at the first I characters of S and the first J characters of T. Okay. So I'm basically saying I'm chopping off some part of S and T every time, and I'm asking you what is the longest common suffix now. Okay. Is this harder than the previous problem? Actually, not so much. Let me just copy this. Put it here. Here's the thing. First of all, I can just spend a lot of time on every query. For every query, I can just do my 2-pointers thing. And then my total runtime would be the number of queries times the length of the strings. But that's bad. I hope I can do better than that. I hope I can do a dynamic programming like the previous case. So given 2 strings of, let's say, length n, I want to solve this in n squared. And then I want to be able to answer all the queries in constant time. Okay. So let's see if I can do something just like before. So I had the longest common subsequence. Can I have the longest common suffix? So I just say longest common suffix of ij is exactly what you would expect. So the length of the longest common suffix if I only have the first I characters of my first string and I only have the first j characters of my second string. And of course, if I can calculate all of these things, whenever I have a query, I just look into my table and I say, this is the answer, right? So how would you do this? Now, I want to find a suffix. So I can do something just like before. I can say, let's say this is I and this is j. I say, does this suffix contain the last letter? It would contain the last letter only if the last letter matches. If the last letter doesn't match, then the answer is just 0, right? So if I have something like this, these 2 strings, they don't have a common suffix. The answer is just 0 because this one ends in H, this one ends in A. But if they do match, so if my I is this one and my J is this one, then I'm matching this last letter with this last letter. And then I have to find the longest common suffix of the first I minus 1 characters here and the first J minus 1 characters here, right? So actually, it's even simpler than the previous one. It's very simple. I just say if Si is equal to Tj, then the longest common suffix Ij is just 1 plus the longest common suffix of I minus 1, J minus 1. Otherwise, it's 0. Longest common suffix Ij is just 0. Okay. And of course, my base case is just like before. If one of my strings is empty, the longest common suffix that they can have has a length of 0. And I can find the suffixes just like before. I can do tracing on my TP. Everything is just like before. And this has the same runtime. Now, why did I give you this problem? Because now I want to give you the next one, which is longest common substring. So substring means that it should appear contiguously, right? So again, my input is the same, 2 strings. But as the output, you should give me the length of the longest common substring. Now, you guessed it, we're going to do something exactly like before, because, I mean, it has worked for us twice. Maybe it would work one other time as well. So I'm going to do the same thing as before, and I'm just going to say I define this. I say longest common substring of Ij is the length of the longest common substring if you have only the first I characters of the first string and the first J characters of the second. My fingers ache. I'm not going to write them again. Okay, it's much easier to type than to write, by the way. So how would I calculate this? I can do something like before again, right? So I say, let's look at this first I characters of S and this first J characters of T. In my longest common substring, I either include the last character from both of them or I don't. If I include the last character from both of them, so I'm including this H and this H, right? So I have to match these two, but then something interesting happens. Because a substring has to be contiguous, if I include this H and this H, then I have to now take a suffix, right? Because that's the only way I can keep it contiguous. So here's the thing. I want to find the longest common substring of I and J. I first say if Si is equal to Tj, then my longest common substring Ij is going to be 1 plus the longest common suffix of I minus 1, J minus 1. So I'm going to use the table that I had from the previous one. But that's not the only choice. Maybe my last characters actually match, but the optimal substring doesn't include the last character. You see, for subsequences, when the last character matched, I could always say that the optimal solution includes the last character. But this is not the case here. Maybe only the last character here matches. It gives me a very short suffix, but then maybe somewhere before there is a much longer match. Okay, so I have to consider that too. But I can say something like before. I'm going to say that, well, if I don't include both of these last characters, if I include at most one of them, then I have either a substring of the first I minus 1 characters of S and the first J characters of T, or the first J minus 1 characters of T and the first I characters of S. Did I say that correctly? I don't know. Okay. So instead of just saying it's this, I say it's the maximum of all of these cases. So longest common substring of the first I minus 1 characters of the first string and the first J characters of the second string, and the longest common substring of the first I characters and J minus 1 here. Okay. So now the case where the letters match is over. If the letters don't match, again, I have a similar situation. So now let's say that was I, this is J. And Si is not the same as Tj. So I cannot put both of them in the solution. So I don't have this case that use suffixes. But I still have the same two other cases here, right? So otherwise, my answer for I and J is just going to be the same thing, except that I only have those two cases. I don't have the first case, which used those suffixes. So just the maximum of these two. Okay. And again, my base cases are when one of my strings is empty and the answer is 2. So this is a nice example because you see that we have now defined two kind of intertwined dynamic programming variables. So I want to find the longest common string, but in order to find the longest common string, I'm also using the longest common suffix. But then I already had a different way of computing the longest common suffix. So I first compute the suffixes, and then I use that to compute this. So computing the suffixes took O(n) squared, assuming that both of them have lengths n. If they have different lengths n and m, then it's O(n)m. And this one is also taking the same time. So my total runtime is O(n) squared, or you can also think of it as O(n)m, where n is the length of S and m is the length of T. Okay. Nice. Now, here's another problem. Let's say that this time I give you only one string, but I tell you that I want you to find a string. I want you to find, let me see, substring or subsequence. It can be either. Let's do with subsequence. So this is what I want to find, longest palindromic subsequence. So in the input, I'm going to give you just one string this time. There is a string S. And in the output, I want you to give me the longest subsequence of S that is a palindrome. And a palindrome is a string that is equal to its reverse. Okay. So for example, something like A, B, C, B, A is a palindrome because you can read it from the end to the beginning or the beginning to the end, and it's the same, right? So as output, I want, again, either the length or the solution itself. So length of the longest subsequence of S that is a palindrome. Now, the dynamic programming that we're going to define here is actually a little bit different, but the ideas are very similar to the previous ones. So let me take my string S here. So I want a subsequence of S and I want it to be a palindrome. So that's equivalent to saying that I want to remove some characters from S so that it becomes a palindrome, and I want to remove as few characters as possible, right? So I could ask it like that, or I could ask it like this. They're the same. But in order to do dynamic programming, it would actually be really hard if you want to only look at prefixes of S. Because before, when we were doing these dynamic programmings, we were only looking at prefixes of S and prefixes of T, right? So the whole point here was that when I was defining, for example, this variable, I was saying, look at the prefix of the first string that has the first I characters. And J was saying, look at the prefix of the second string that has the first J characters. But that kind of thing would probably not work here. So I'm going to define a different thing. I'm going to say, let's say the answer, again, I'm going to have two indices on I and J, is going to be the longest palindromic subsequence if I only have the characters from index I to index J. So instead of just chopping off something from the end of my string, I'm chopping off something from the beginning and something from the end. Okay, so this is going to be the length of the longest palindromic subsequence if I only have the characters from index I to index J. Okay, so I have something like this. Let's say this is my index I, this is my index J, and the subproblem that I'm defining is I'm saying forget about everything before index I and forget about everything after index J. What is the longest palindromic subsequence that you can find in this middle part? Okay, so that's what I'm calling ANSI J. Now, just like before, I can find a recursive or recurrence formula for my ANSI J's. So here's the thing. Let's say my I is here and my J is here. So my string starts with a T and also ends with a T. Now, again, just like the lecture on greedy algorithms, I can prove that it's optimal to match this T with this T, right? Because if you don't do this, you're either not matching any of these two t's, in which case you could have matched them and have a longer palindromic subsequence, or you're matching only one of them with some other t, but then you can match it with this t instead. So that's the general vibe of the idea here. So I can say, just like before, I can say if Si is equal to Sj, then the answer Ij is just going to be, well, 2, because I'm matching this one with this one, so there are 2 characters, plus the answer from I minus 1 to j minus 1. Okay, except for one case, yes. If I itself is equal to j, then these 2 characters are actually the same character, right? So you have to be careful. Yeah, this was also I plus 1 j minus 1. So I don't have character I and I don't have character j anymore. So I have from I plus 1 to j minus 1. You're right. But yeah, we will talk about the base cases at the end. So for now, we're assuming that we have a long string. But what if they don't match? So let's say my I is here, but my j is here. So I have an S and a T. Now, again, just like before, I can say that in my solution, I cannot have both of them because T is going to be the first character and S is going to be the last character, and they don't match, so that would not be a palindrome, right? And because I cannot have both of them, I can have at most one of them. So I can again say that my answer on Ij is going to be the maximum of the 2 cases. The first case is the case where I don't have I, so the answer from I plus 1 to j. And the second case is where I don't have character j, so the answer from I to j minus 1. Okay. Yes, I have my recurrence relations now. What are my base cases? My base cases are, if I have an empty string, the longest palindromic subsequence is just the empty string. If I have a string with 1 character, the longest palindromic subsequence is just that 1 character, right? So those are my base cases now. But very interestingly, I have to be careful about the order in which I calculate my dynamic programming results, my results for my subproblems. Because remember, every time when I'm calculating the answer for Ij, I need this one and this one to be already there. So I need to have this topological sorting, but as you see, answer for Ij actually depends on the answer for I plus 1j. So I cannot just go in the order of increasing I, because in that case, I have not yet calculated answer of I plus 1j when I'm calculating answer of I. And also it depends on answer of Ij minus 1. So how do we order our calculations? Yes, you can do it by the length of the string. Because every time when you're finding the answer from I to j, so this has some length, but then this string has a length that is 1 less. And this one also has a length that is 1 less. This one has 2 fewer letters. So you have to sort these things based on the length of the string. So basically when you're doing, let's say, some for loops, you have to say for every I from 0 to n, and then you have to say for every length from 1 to, let's say, n, j becomes I plus L minus 1, right? And then you calculate the answer for Ij like that. Right? But the order is really important. You have to do it in the order of lengths. And also you could put the lengths first. So you can also do something like this. You can say for every length from 1 to n, and then for every starting point I from, let's say our indices are starting from 1 to, now here's the thing. I have to say, I would do it like this. I prefer C++ now suddenly. I have to say that I plus the length minus 1 is less than or equal to n. Right. Then I find my j, and then I calculate the answer ij according to this formula. But the order really matters. Again, if you remember one thing from the DP sessions in this course, it's that the order matters. Okay. We are running out of time, so I'm just going to give you some other problems that I want you to solve. So in all of these problems, the input is similar to before. So these are homework, but they don't contribute to your grade. So just do it on your own. We saw how to find the longest palindromic subsequence. What if I want the longest palindromic substring? Can you find this one? Okay. So in all of these homeworks, my input is just one string S. Okay. So I give you one string S. I ask you what is the longest palindromic substring of this string. So not a subsequence, but a substring. The other thing that is interesting is this one. Let's say I ask you for the longest repeated substring. Okay. So a substring that is somehow appearing twice, and they don't have to be disjoint. Okay. So for example, here, I have to be here. I also have to be here. So to be is a repeated substring. But also, if I had a string like this, A, then AA would be a repeated substring because it appears at two different positions. Even if they intersect, it's fine. Okay. So the question I want you to solve is this. I want you to output the length of the longest repeated substring given a string S. And of course, you can imagine that we can do longest repeated subsequence. That would also be interesting. Yeah, these three are enough. So just solve these three and figure out how you can solve them in a way similar to all these previous algorithms that we saw. So the ideas are very similar. The ideas are that you have to just somehow look into substrings that are obtained by removing some prefix and some suffix, and then define subproblems on them, find the relationship between those subproblems, and so on. So that's it. I'll see you tomorrow.